Welcome everyone to the QuMat seminar. A pleasure to introduce my old friend Paul Haney. We shared, we were office mates when I was in Texas a long time ago. And then Paul graduated in 2007, went to NIST Gaithersburg as a postdoc, and then basically stayed on there as a researcher and is now a project leader at NIST. And he's an expert in especially ab initio methods applied to spintronics, I would say. So please take it away, Paul.
Awesome. Hey, thanks, Randberg. Thanks for the invitation. This is my first time in the Netherlands, so it's really great to be here and see this this great place. And so, okay, let's see. Yeah, so the title of my talk is Orbital Magnetism in Moiré Superlattices, as revealed by Landau Level spectroscopy. This work is really a joint experimental theory modeling work. And so I'm sort of on the theory modeling side of things. And I want to start by thanking my experimental colleagues at NIST. And so this is from the group of Joe Strosio. And particularly highlighted here are the folks who were involved in this. So there's Yulia Maximenko, there's Joe, there's Moiré Superlattices, which people know here. And then this is Nikolai Zhivnia. And this talk is really going to be a deep dive into this project we recently completed on this Moiré systems. And so before I go into all of the details of that, I did want to mention just some other topics that I've been interested in lately in case there's any overlap and people would like to discuss more. More recently, I've been looking at spin orbit torques. So that's a phenomenon where you have a current-induced magnetic dynamics. And in particular, looking at the effects of systems with lower symmetry and the effect of that on the spin orbit torque. So in particular, if you have substrates with non-symmorphic symmetry, or if you have antiferromagnets, or the single layer ferromagnets with C3 symmetry. And then also recently thinking about orbital currents in spintronic devices. So you probably are familiar with the notion of a spin current. And so the idea is, can you generalize that to an orbital current? And to what extent would such a quantity influence spin orbit torques and magnetic dynamics? And what we're thinking about really now is trying to calculate these or model these measurements where people use optical experiments to measure orbital accumulation, and which is currently interpreted as related to the orbital Hall effect. But I'm actually not going to talk about these things today. As I mentioned, let me know if you'd like to discuss further. Today, I'm going to talk about this project. And the takeaway message of the talk is that Moiré materials have unique orbital magnetic properties. And what I mean specifically by that, in this case, is an orbital magnetization in the two valleys, which is equal and opposite. And also orbital magnetic susceptibility, which varies very rapidly with energy. And I want to show you that these magnetic properties can be fairly directly accessed using Landau level spectroscopy. And I'll explain how that works. So here's the outline. And really in this talk, I'm going to assume very little prior knowledge. So I'll be starting from the basics and building upwards. And the first part of the talk, I'm going to discuss Moiré graphene systems in general and orbital magnetization in general. And then I'll move on and talk about Landau level spectroscopy and how you can use a semiclassical analysis to extract information about magnetic response functions. And then I'll show some calculations which illustrate how this Landau level spectroscopy kind of works in a model. So the first part of the talk is just sort of background and then the theory calculations. And then the second part of the talk, I'll move on to discuss the experiments. And in the experiments, we sort of analyze what's going on at different levels of semiclassical approximation. So at the 0th level, we can learn about the density of states, as we'll see. At the first order, we can learn about this orbital magnetization, which is present in the material. And then at the second order in approximation, finally, we can learn about this magnetic susceptibility. So you've probably heard of this twisted bilayer graphene by now. And so what we do is we start with a Bernal stacked graphene bilayer. And so the two graphene monolayers are in registry with each other. And then if I apply a small twist to one of them, if you squint your eyes, you can see the formation of these long wavelength Moiré type patterns. And in 2011, Bistritzer and McDonald predicted that at this so-called magic angle, the energy bands near the Fermi level get quite flat. And that's interesting because when you have a small bandwidth, that means your kinetic energy is very small. And so your interaction energy is relatively very big. But when you have strong interactions, you can get these symmetry broken states and strongly correlated physics controlling the behavior, which is quite interesting to look at. So several years later, Pablo Herrera fabricated one of these devices. And when he looked at the phase diagram versus carrier density and temperature, sure enough, he saw lots of interesting phases, such as the superconducting phase, this correlated insulator state. And that really kicked off this field. And it's been a very big research effort since then. So some of the early papers, which also stand out from my point of view, showed that the twisted bilayer graphene, if you put it on an HBN substrate, and at certain filling factors, could be ferromagnetic. And moreover, that in certain cases, it demonstrated this quantum anomalous Hall effect. So that's a quantized Hall effect in the absence of a magnetic field. And at NIST, we're interested in standards. So we're thinking about this, using this type of device for metrology applications, such as a resistance standard. Okay, so things have just sort of continued since then. So people have varied the number of graphene layers and the twisting angle configuration between them, and seen again all sorts of interesting stuff, unconventional superconductivity and other things. And you can also use not just graphene, but transition metal dichalcogenides. If you have like a heterostructure of these two different type of TMDs, the lattice mismatch can be enough to form this Moiré pattern of stacking. And again, people observed this quantum anomalous Hall effect in these TMD systems. And they've also observed interesting spintronic effects in these Moiré TMD systems, such as spin Hall effect and spin accumulation, as well as spin orbit torque. So it's a pretty vast field at this point. And the particular kind of Moiré system that we'll talk about today is twisted double bilayer graphene. And so what we have is two AB stacked graphene bilayers and then a twist angle in between the two bilayers. And so that leads to this pattern of long wavelength pattern of different stacking arrangements in space. So you go from AB, AB, ABBA, ABCA. And these are just referring to different translations between subsequent graphene layers. So the magic angle for this particular system is about 1.3 degrees, it turns out. And people have studied this system quite a bit as well and seen superconductivity and all sorts of interesting stuff. So the angle that we actually study in the work I'll show is rather away from the magic angle. It's like 1.75 degrees. So it's not a well-studied angle range. So there might be something new to learn. And the bands aren't particularly flat, but more narrow. Yeah.
I have a question about the magic angle. So I mean, we always say there's this magic angle, but is it guaranteed that this always exists in these Moiré superlattices, or is it just a fluke of graphene or graphene-like lattices?
Yeah, so I would say it's not guaranteed. So it seems particular to graphene. I would say that like as you change the angle and it becomes small, your bands, your mini Brillouin zone gets smaller and smaller as your unit cell gets bigger and bigger, and the bands start to just change very rapidly. And so you can have configurations where, so you're sampling like a very large number of possible band structures. In the case of graphene, I'll actually show in a couple of slides sort of the mechanism, hand-wave mechanism by which you get very flat bands. But it's not the case that you'll always get flat bands for any Moiré system. Yeah. Okay. So what I want to do actually now is build up this system piece by piece and develop some understanding of the electronic structure. And actually, I'll start with just monolayer graphene. Okay. And so this is something you've probably seen before. So we just have a honeycomb lattice with two atoms per unit cell, sites A and B. And for this lattice structure, you can represent the Brillouin zone as a hexagon, and all the action is going to be happening at these K and K prime high symmetry points away from the gamma point. And if I look at the graphene band structure near this K point, you have a linear dispersion, and so these linear bands cross at the so-called Dirac point here. And the low energy effective model for the system is shown here, and this is a model in AB space. So it's a two-dimensional model in this sublattice space. You see you have this linear dispersion, and sigma here is a pseudo spin for sublattice. And so this is for one of the values, say the K value. Okay, so there's a Hamiltonian. I can write down the wave function for a given block momentum K, where K is measured from the capital K point. And again, this is sort of a pseudo spin, so the relative phase between these is telling me the relative phase between wave function on site A and B. And if I represent this in K space, what you see is that the pseudo spin acquires this helical type structure, where the pseudo spin is aligned with the K vector, like this. So this is actually an interesting electronic structure. You might remember that in general, if you have like a spin half fermion and you rotate its spin by 360 degrees, it doesn't come back on the exact same wave function. You pick up a factor of -1. And so if you're going around this loop in K space and you return here, you acquire this phase -1, which is EVI pi. And so that means that there's a pi vary phase associated with this loop in K space. Because vary phase is by definition nothing but the phase factor acquired after traversing a closed loop under certain assumptions of adiabaticity and so on. So I point this out because vary phase is going to be showing up a couple times later in the talk. So it's important in general in evaluating the position operator and subsequently the orbital magnetization. And it's also going to show up in the Landau Level spectrum. Okay, so now let's move on to Bernal stacked, just normal bilayer graphene. So typically the A side of one layer is on top of the B side of the other layer. And in this case, the bands acquire some quadratic type dispersion, and there's still no band gap. But if you apply a displacement electric field, a displacement field or an electric field perpendicular to the plane so that these two layers have a different on-site potential energy difference, then you open up a gap. So let's start with this Bernal stacked layer. And so we have a Brillouin zone, if you will, for top and bottom, and the K points are aligned with each other. And then when I twist one of the layers a little bit in real space, the reciprocal lattice will twist a little bit, or the reciprocal unit cell will twist as well. And so the K point of the bottom and top are no longer aligned with each other. And we'll form these so-called mini Brillouin zones. So all of the behavior that's occurring at the long length scale of the Moiré pattern is being described in this small region in reciprocal space. And if I zoom into this K point here, what you'll notice is that if you're like an electron, let's say in the bottom layer, exactly at the Dirac point of the bottom layer, and then you tunnel to the top layer, all of a sudden you're not at the Dirac point of the top layer anymore. You're displaced from it. And so there's sort of like an effective momentum shift associated with interlayer hopping in this case. And that the amount of that momentum shift is related to the displacement, which is related to the angle. And so if I write down the tunneling matrix element between top and bottom, you have some amplitude to hop from A to A, B to B, A to B. And importantly, you pick up this phase factor from that effective momentum shift here. And there's a couple other additional momentum shifts related to these other symmetry connected K values in the Brillouin zone. So the details of all these numbers don't really matter. I just show this to illustrate that this is the Moiré potential that's describing the modulation of the lattice in real space. And the smallness of these G's is what leads to the large length of the Moiré potential. Okay, and so now we can sort of wave our hands a little bit as to why graphene requires flat bands. So we had this twisted graphene bilayer. So the top and bottom Dirac points are displaced from each other by some amount related to the angle. Initially, let's suppose they're uncoupled, so these linear dispersing bands will just cross at some point, and at some energy, E naught, given by that expression there. And then when I turn on interlayer coupling, that leads to an avoided crossing at this degenerate point, with some size 2W, let's say, where W is interlayer hopping. And you can imagine that you can try to tune things so that this initially degenerate point gets pushed down to the 0 energy level. And so then maybe you would have something where there's like lots of states near 0 energy. And so that would be the condition that you would want to satisfy. When you put in the known values for these parameters from bilayer graphene, you would estimate a magic angle, quote unquote, of 1.5 degrees, which is in the ballpark. But I will say this is quite hand wavy. It doesn't explain why the bands would be flat everywhere in Brillouin zone. And that's actually like a tricky thing to understand. It's not very obvious thing. Okay, so we're going to move on and talk some more about the electronic structure of these twisted systems, and in particular, their orbital magnetic properties. So before I do that, I just want to have 2 slides talking about orbital magnetism, just so we're on the same page there. So here we have orbital magnetism. So classically, it's just describing the magnetic dipole moment associated with a charged particle going in a closed orbit, right? And it turns out that the theory of orbital magnetization in solids was only developed in the 2000s. And the reason why it took so long is because there's some subtleties in evaluating this position operator in periodic systems. So the position is unbounded, and so it's sort of incompatible with periodic boundary conditions, which are the bedrock of like the way we formulate things. So figuring out these subtleties is what led David Vanderbilt in the 90s to develop this modern theory of electric polarization. And then applying it to this orbital moment in the 2000s, Ivo Souza and Vanderbilt developed this modern theory of orbital magnetization. And then simultaneously, Chen Nu and Di Zhao use a semiclassical approach to develop the same thing, and the 2 are equivalent. So I just write down the final expression for the orbital magnetization here. And I just want to point out that it can be written as a sum of 2 contributions, where this first contribution can be interpreted semiclassically as a self-rotation of the wave packet. So you can think of this as just the electron spinning around in a closed loop. And then there's a second term here, which is associated with this Berry phase modification of the density of states in a magnetic field, which was developed by Chen Nu. And this can be related to, in some cases, the presence of chiral edge states and their contribution to the orbital magnetization. And this quantity that's entering this term here is the so-called Berry curvature. And I'll be showing some plots of the Berry curvature here throughout the talk. And so the Berry curvature, you can understand in some sense as making some contribution to the orbital moment. And so, yeah, throughout the talk, I'll be at times maybe a little sloppy about Berry curvature versus orbital moment, but the 2 have some relationship with each other. So just a word about Berry curvature, in case it's something that you're not super familiar with. If you want to think about it in just very concrete terms, you can think about it as the transverse conductivity of a block state at some wave vector k. So if you have an applied field pointing upwards, due to the properties of the band structure, you can have transverse velocity response, transverse conductivity. And that is given by, up to a constant, the Berry curvature. More mathematical sense, the Berry curvature at a K point in a, like, let's say, 2-level system would be the area subtended by the spinner, the solid angle subtended by the spinner when you go around a tiny loop in K space, in case that's a useful way to think about it. And I'll finally point out that the Berry curvature has some symmetry requirements to be broken time reversal symmetry or broken inversion symmetry. And finally, I'll mention that this Berry curvature is related to the Berry phase I talked about a couple slides ago. In particular, the Berry phase associated with a closed loop is equal to the Berry curvature, the integrated Berry curvature inside the loop. Okay, So with all of that in mind, let's move on to our twisted double bilayer graphene. And so here's a structure. Here's a depiction again of the stacking configuration in real space. And you'll notice that there's a symmetry. I can do a twofold rotation about the y-axis, and the lattice returns back to itself. And this symmetry implies that the total Berry curvature at the K and K prime values will vanish, and also that the orbital magnetization will vanish. But when I apply this vertical electric field or displacement field, I break that symmetry. And so now I can have a non-zero Berry curvature at the K and K prime values, but it must be opposite because of time reversal symmetry. And so that's sort of this valley contrasting orbital magnetization I was talking about. We can turn on and off orbital magnetization to two valleys with this displacement field, which experimentally would be at gate voltage. So now finally, let me show you some electronic structure of this twisted double bilayer graphene. So this is in one of the mini Brane zones. And what you'll notice is that there's these two bands near the Fermi level, which are rather isolated from the other set of bands. So there's a valence and conduction band. In this talk, we'll be focused on the valence band. So that's where our attention will be. And on the color code is the Berry curvature. So the Berry curvature you see is peaked near these small band gaps. And there is a band gap at U=0 here. And you notice this doesn't resemble at all the quadratic dispersion of normal bilayer graphene. So the Moiré potential is really controlling the band structure here. And here's a plot of the Berry curvature in the mini Brane zone. And you'll notice that the total Berry curvature is 0, as required by that symmetry. And we have some hot spots here at the top and bottom coming from the trigonal warping of the band structure. Now, when I add a potential difference between top and bottom layer, you'll notice that the valence band changes quite a bit. So the band structure is quite tunable with the gate voltage. We'll see that in the experiment. And then also you'll see that now the total Berry curvature in the mini Brane zone is non-zero. Yeah.
Is there an easy way to understand why why applying this voltage breaks this symmetry between K and K prime? Just let's say I would have expected it. The graph on the top right, you see a marked difference in the
Yeah. So let's see. So here's K and K prime, right? And so when I have this twofold rotational symmetry, I can apply that symmetry. This will get rotated into that.
Yeah.
And so that's why this positive orbital magnetization gets turned into a negative. But now I don't have that symmetry anymore. And so K and K prime are no longer symmetry connected. And so that's why there's a difference between K and K prime. Yeah.
Yeah. Okay.
Okay. So I'm going to. Let me mention just for orientation that we're looking at one mini Brane zone. There it is. There's another one way over there, and it has an opposite Berry curvature from time reversal symmetry. So similarly, we have a positive orbital moment here, negative there, and then if we apply a magnetic field, we can split these moments because of Zeeman splitting. So we'll see that later in the experiment. Okay, so now I'm going to move on and talk about Landau level spectroscopy and how that can be used under. Oh yeah, sure.
This let's say this local with the local orbital magnetic orbit, you cannot be Berry curvature then, or is it?
Oh yeah, so
Someone is spoken of the build. I think
Yeah.
in the end it's only valid if you integrate over everything. Or let's say there's some issues with interpreting it locally, I think.
yeah, so well, let's say this is the Berry curvature in K space, and so of that band. And so what you would need for the orbital moment is the total Berry curvature integrated up to some Fermi level. And then there's an additional piece coming from the self-rotation of the wave packet, which I don't have plotted here. And so it would be those two contributions that would lead to whatever this value ends up being. Yeah. So I'm not sure if that answers your question.
Yeah, I'm wondering if it's maybe it's actually something that's really observed a little bit, or whether it's more like a theoretical thing that you define somehow as being, let's say, taking this expression and evaluating some part of it over some part of the real zone.
Yeah. Oh, like as far as like this distinction I'm making, if that's observable or?
Now, whether it's actually, whether, for example, you can experimentally observe the optimization really in one part of the real enzyme, whether
Oh,
you
I
always
see.
observe the total.
I see what you mean. Yeah. So, so no, like because they're connected by time reversal symmetry, there's no spatial separation between them.
Right.
And so in the absence of a magnetic field, it's not detectable.
Yeah.
So that's why you kind of need this magnetic field, which breaks the degeneracy between the K and K prime valley. And then you can like address those valleys individually because they have different energies.
Yeah.
Okay. Yeah, so let me now move on and talk about Landau level spectroscopy. And again, I'm starting from ground up. So so when you turn on a magnetic field, we form these cyclotron orbits. And area of the orbit is given by this magnetic length squared, which is inversely proportional to the magnetic field. And all of these orbits, if they're of the same type, are degenerate. And so the Landau level degeneracy is macroscopic, which is given by the number of these orbits that you can fit inside your sample. Now, as I increase the magnetic field, my orbits get tighter and tighter. And so my Landau level degeneracy, I can fit more of them, gets bigger and bigger. And because I'm going in a closed loop, I have this requirement that the phase accumulation acquired by the electron is an integer multiple of 2 pi. And so that leads to this semiclassical quantization condition that the total phase accumulation, which has this kinetic phase and Aronoff Bohm, and it's actually not, for Landau levels, it's not 2 pi n. It's 2 pi n plus half. There's a so-called Maslov phase associated with turning points of the semiclassical analysis. So what's important there is that the energy levels will then be discretized because there's only certain energies for which you can get this phase matching condition, like in atomic physics. So these closed orbits of real space correspond or have a corresponding closed orbit in K space. And so I can write down this phase accumulation associated with a closed orbit in real space of an electron at some energy En, say. It turns out that that is equal to the K-space area of the equal energy contour at that energy En times h over qb. And that again has to be 2 pi n plus half. So if I have some dispersion, energy versus K, and these different K-space energies, and I apply a magnetic field, there's only certain energies which match this or satisfy this quantization requirement, and I can label them with this Landau level index n. And so experimentally, you apply a magnetic field, you can measure these discrete levels, you can count their index, and in that way measure out the K-space area versus energy of your electronic structure. So here's sort of a cartoon illustrating how this works. An energy dispersion, which is in this region of K-space dispersing upwards, so electron-like, then it reaches a saddle point, and now it's dispersing downwards, so it's hole-like. And so if I plot the K-space area of isoenergy contours versus energy, you see they get bigger and bigger, saddle point, and then smaller and smaller. And this quantization condition, again, is just that this K-space area it can be written as n plus half over b by phi naught, where phi naught is a flux quantum. And so there's discrete energies which match this condition. And so for a given magnetic field, you can just write down these energy values in their corresponding Landau level index. And these are electron-like Landau levels, and these are hole-like. And so as I increase the magnetic field, orbits get smaller, degeneracy gets higher, and I need less Landau levels to fill in all the states of my band. And so as well, the required or the energy levels which satisfy the condition change, and so I get a new set of energies for a different field. And in general, you get this family of curves of Landau level energy versus magnetic field. And this is actually a pretty direct measurement of the K-space area or integrated density of states. So if I just rescale these different Landau levels according to some factor related to their index, they actually all collapse onto a single curve, which is exactly this area versus energy curve. And so that's how you can map out this K-space. So that's a 0th order semiclassical approximation for Landau levels. But it's not the end of the story because here's our first quantization condition. But when we go around the closed loop, remember that there are other contributions to the phase accumulation, like the Berry phase that I mentioned earlier. So to this phase accumulation, you need to add all the contributors, including the Berry phase, and that must be equal to 2 pi n plus half. And so in the case of graphene, this is leads to this well-known effect. We remember that the Berry phase of graphene was pi, and this factor of pi cancels the Maslov phase contribution. And so now for graphene, it's not 2 pi n plus half, it's just 2 pi n. And so for n equals 0, that's what leads to this zero energy level for the graphene lowest Landau level. But this Berry phase contribution is actually just a part of the contribution from the orbital magnetic moment. So that's what I'll describe here. So like here again, it's a K-space area versus energy. We have this condition for satisfying the quantization condition, which leads to these energy levels. But one way to think about the orbital moment contribution to this is that when you apply a magnetic field, you can have some Zeeman coupling to states with magnetization. And so that will shift their sort of smooth part of their energy eigenvalues according to that Zeeman coupling. So this is the orbital moment of states at some energy En. And suppose, for example, all the states had a positive orbital moment. That would shift all of the energies because of this Zeeman coupling. And so we need to account for that shift in our quantization rule. And so that's what leads to this first order correction. So the orbital moment of states at En is just given by this expression I showed earlier for the orbital magnetization. And then to get this value at a specific energy, E, we take its energy derivative here, or derivative with respect to chemical potential. And you'll notice the second term here, when we take this energy derivative, this is going to give us the Berry phase. This is going to be the connection between the Berry phase and the orbital magnetization. So in general, this is the first order correction, and it's coming from the orbital moment and the way the orbital moment shifts the energy levels. But there can be higher order corrections as well. So a field doesn't just change energies according to first order, it can change energy from second order through the magnetic susceptibility, for example, and onward it goes. And so recently Chen Nu and his student Gao derived this sort of extended Onsager relationship, which is valid to all orders in magnetic field. And we see here that here is the initial quantization condition. This is the zeroth approximation of just looking at K-space areas. There's from the Zeeman splitting, and here's now from the susceptibility. So chi prime is the energy derivative of the magnetic susceptibility. So this was derived in the 60s by Roth, but only recently was it recognized that these coefficients are just magnetic response functions. And so if you have a Landau level spectrum that you can, from which you can identify these corrections, you can extract magnetic response functions to any order in principle. And then conversely, if you know the magnetic response functions, you can accurately predict Landau level spectrum. So in the remaining part of this theory section, that's what I'll do. So I compute all these magnetic response functions, and then I can use this rule to get the semiclassical Landau level spectrum. I can compare that to the exact or quantum mechanical Landau level spectrum, and from that determine the relative importance of different orders of correction. So I won't go through details of how we compute the spectrum quantum mechanically. I'll just show you the final answer. And so, we introduce this vector potential into our Hamiltonian, and we end up with this energy spectrum as a function of magnetic field shown here. And this is like the Hofstadter butterfly type of pattern. And the experimental part, experiments take place in this range from 0 to 15 Tesla. So that's about less than a quarter flux per unit cell. And this energy range here, this is the valence band. So that's what we'll be focusing. And you can see that for lower fields, the spectrum is basically resembling that of just Landau levels. So in that case, the semiclassical approximation is describing the spectrum. Now, at some point, a certain flux per unit cell, the semiclassical model just doesn't work at all. It's like not applicable. And so that's shown here. And so you can see that as you're approaching 1/2 flux per unit cell, you're really in this Hofstadter regime where things are quite different. Okay, so this was a zoom in now of that quantum mechanically computed spectrum. This is for a non-zero displacement field, so I have equal and opposite orbital moments in the two valleys. And so you can see that at the two valleys, I get different spectrum because of that zoom-in coupling. Now, if I compare that to the 0th order semiclassical, right? So if I just have a K-space area, I can get the 0th order. That's shown in the blue lines there. And you see that the agreement's not great, but particularly for the 0th Landau level. And certainly the 0th order doesn't capture the valley splitting at all. So if I move on and consider the 2nd order correction, so include the orbital magnetization, I at least obtain the valley splitting, but still like pretty big disagreement for the 0th Landau level. But now when I compute the magnetic susceptibility, which I won't go into those details, now I get pretty good agreement. And so what we see is that in just theory land, when we're looking at the quantum mechanical versus semiclassical, the 2nd order correction is quite visible in the description of the system. And we'll see the exact same thing in the experiment. Okay. Yeah. Okay, so now let me move on to the experimental part. So in the experiment, we're doing scanning tunneling microscopy. And so this is a measurement of the local density of states. And so we have a tip here. Here's the substrate in the sample, and we have a backgate. And so by applying a voltage on the backgate, we can change the displacement field, and we also simultaneously change the filling of the system. So we change the carrier density. We can image the real space Moiré lattice directly. And so from that, we can figure out the twist angle pretty straightforwardly. And that's where we get this twist angle of 1.74 degrees. And just to give you a sense of the way the data is structured, this is a so-called gate map. And so when we change the backgate voltage, like I mentioned, we change the vertical displacement field. So that's shown in this axis. We simultaneously change the band filling, that's shown here. And then as we vary the tip bias, we'll be probing different parts of the energy spectrum above and below the Fermi energy here. And here's again this plot that I showed in the last slide. And here is the calculated local density of states at the top layer. And we can start to identify the broad features in this gate map and relate them to the band structure. So I don't know if you can see it on the screen very well, but there's some broad feature along here and here. So that's identified as this valence and conduction band. And if we zoom into, for example, displacement field of 0, so that would put us right there. That corresponds to hole filling. And so we're at this point in the band structure. So we're near the flat part of this band, in this case, where the density of states is quite high. And that's why we get this peak. And we end up being pinned to that high density of states as we vary the gate voltage. And then similarly here at point 2, we end up in the conduction band, again, pinned to this flat region where we have high density of states. Now, one thing you can notice, there's like this feature moving down in the valence band as I increase the displacement field. So that feature is coming from this flat part of the conduction band, or sorry, the valence band. You notice that as I increase the displacement field, this flat part of the valence band is moving down in energy through the valence band. And that's what's seen here. You can't really see it as well in the theory. But when we turn on a magnetic field, now we split this continuum of levels, continuum of states into Landau levels. And again, you can see theory and experimental comparison. And as we increase the magnetic field, Landau level spacing gets bigger, and number of Landau levels decreases.
Can I ask maybe a naive question here? So the experiment is done locally.
Yeah.
And I mean, you mentioned that the number of Landau levels, I mean, you have them globally packed somewhere. Is there any spatial variation? Do you know?
Not much.
Not much.
Yeah, so like everything I'm showing here is on one of the sites, like AA site stacking.
Okay.
And we looked at like spatial maps to see if there was something interesting spatially happening. Not a lot of variation, actually.
Okay.
Also not really in the calculations.
No. Okay.
Yeah.
Thanks.
Yeah.
Question about also sizes now. So that's the localization length, it's the magnetic length. of
Yeah.
the point. Since your Moiré stone is pretty large.
Yeah.
What is actually the magnetic length? Is it larger than, like, normally you talk about 4 nanometers high?
Yeah.
What's the size here actually?
Yeah. So you can see that in this plot here. Yeah. So we're down here. And you can see this is a flux per unit cell. So this is how many Landau levels I fit in the unit cell. And so less than 1, 0.25. So Landau level area is bigger. As we're getting at the highest fields we do, like 15 Tesla, we're starting to get into the regime where the Landau level is getting closer to the unit cell size, but we never get there. Okay, so yeah, here's another way of looking at the data here where we just have fixed displacement field, we vary the magnetic field, and then we look at the spectrum. So this is like the cartoon I showed a while back. And this part's the valence band. And so here's the whole leg levels moving upward in energy. Sorry, the electron leg levels moving upward in energy. There's the whole levels and they annihilate at the saddle point. And then again, that changes with displacement field. So this is like, the 0th order, we see some qualitative features of the electronic structure varies with displacement field. And when we try to do something more quantitative, like getting the K-space area, this is what we find. So here is a Landau level spectrum again versus magnetic field. And as I mentioned a while ago, if you just rescale all these Landau levels according to their index, it should just collapse on a single curve and give you the K-space area versus energy, but it doesn't, okay? And so that's one of the kind of indicators that this 0th order Onsager condition is not adequate to describe the Landau level spectrum that we have. So let me talk then about these correction terms. So in the 1st order correction is going to come from the valley contrasting orbital magnetization. And so this, you've seen this before. We're just going to have a large displacement field, equal and opposite orbital moments, and we're just measuring the Zeeman splitting. So here's the experimental data. These are traces as we're increasing the magnetic field, and you see in this 0th Landau level, the emergence of these 2 peaks, which are splitting in energy as I increase the magnetic field, and that's shown in this data here. And then on the theory side, we can also compute this splitting. So this light gray curve is for 0 temperature calculation. And you can see that, again, we get a similar type of splitting in the calculation. So this corresponds to a G factor of like 5 or 6. Now, one thing that's interesting is that the highest fields shown here, we start to see the emergence of these magnetic subbands, or the beginning of this Hofstadter bands. Now, when I broaden out the calculations to sort of match the experimental broadening, you just get this like broad kind of like blob here. And you can start to see maybe hints of that at the experimental data on these like little peaks within this 0th Landau level. And now if we move on to the 2nd order analysis, so this is what I showed a couple of slides ago. And this is not going to be due to this 1st order correction because actually the displacement field for this data was pretty small. So there is no orbital moment in this case because I've tuned myself away from it. But we can just use this correction term that I talked about earlier, chi prime, and now we just have 2 unknowns, K-space area and chi prime. So we have 2 unknowns, so we need 2 equations. So at a fixed energy, I just need to have 2 Landau levels, and I can solve these equations for S and chi prime. That's what you get. So what we do is that for every energy, we solve these equations for all pairs of Landau levels and get S and chi prime as a function of energy. And this is what you get. So now this area, k-space area versus energy does collapse onto a single curve. So that's an indication that things are making better sense. Again, if you compare to the theory, there's some agreement. There's like an energy shift, but that's just related to an overall energy level of the calculation. And when you look at the chi prime, you see it collapses not like onto a completely continuous curve. There's like a little jump there, but still nonetheless, it collapses onto a curve which is somewhat in agreement with the experimentally computed chi prime there. So what's nice about this approach is that in order to extract these material parameters from the data, there's really no modeling you need. You're just doing like simple algebra directly from the data points, and you're getting out these detailed magnetic response functions as a function of energy, which is nice. Okay, so the orbital susceptibility is playing a large role, and well, magnetic orbital susceptibility is sort of its own world unto itself. There's a lot of different microscopic mechanisms for this susceptibility, and so some of the well-known ones include the Landau Peierls contribution, Van Vliet contribution, and again, more recently, the group of Chen New have identified additional sources of orbital magnetic susceptibility, again related to this Berry curvature and quantum geometry. So for example, when you have orbital magnetization, you can get Pauli paramagnetic susceptibility from that orbital magnetization, as well as contributions from the so-called quantum metric. So when you look at in the calculation, all of these different contributions to the chi prime, the variation of susceptibility with energy, you see that it's a quite complicated mixture of them, but these quantum geometry derived contributions are particularly large at the top of the valence band where the Berry curvature is large. Now, one thing we can say more generally, I think, is that Moiré materials can be expected to have a large chi prime in general. So here's a calculation of the maximum chi prime as a function of Moiré lattice period. So in the calculation, I can just reduce my twist angle. I get bigger and bigger unit cells, and then I see how big does the susceptibility variation with energy, how big does it get? And you see that it gets bigger and bigger as you make your unit cell bigger. And that can be understood, I think, on really dimensional analysis grounds. So here's a susceptibility. It's dm by dv. And the orbital magnetization density is the phi for area. When you work it out, you end up with something which is roughly scale invariant. So as you make your unit cell bigger, you can imagine that the orbits can get bigger and bigger. So that would give you a bigger orbital moment. But the thing is, when you make your unit cell big, the hopping gets smaller. And so that sort of sets the scale for the current. And so they go slower and slower. And you end up with something that's rather scale invariant. But what matters is not chi, but the variation of chi with energy. And that just goes as a squared. So as you move a little bit in energy, that the orbital magnetization susceptibility can vary quite a lot. So what we're just starting to think about now are what the potential implications of that could be. So for example, if you had a Moiré system and some disordered potential, let's say from like long range Coulomb interactions, so that the Fermi level is in different parts of the bands, then when you apply a magnetic field, the susceptibility or the magnetization that you develop would vary quite a lot at different points in space. And so you would develop these microscopic currents. These aren't transport currents or anything, but nonetheless microscopic currents. And we're thinking about the implications of that. And also about whether or not this would be important for not a magnetic field, external field, but if you have spontaneously magnetically ordered state, if you would have some fluctuations in the properties of the orbital magnetization, and what that might mean for things like the quantized levels. Okay, so that's it. So that's my talk, and there's a conclusion again. Thank you very much.
Thanks very much, Paul. I think your talk was connected to experimental activities, but also theoretical activities here. There are already a lot of questions. I think I was wondering if there are more questions. So raise your hands. Okay.
Yeah, so maybe a very naive question, but you showed that, okay, so the let's say by applying a gate voltage, you introduce some asymmetries. And I was wondering, a lot of like 2D materials would also have stacking. Yeah, or let's say would also have a vertical buckling. For example, if you would have germanium or whatever, like, would you, what kind of effects would you expect if you would start stacking like the twisted bilayers or bilayers of buckled materials on top of each other? Like, because I would imagine that that also could introduce some kind of a like local voltage between the.
Oh, yeah, I see. So, yeah, so it'd be like having a effective displacement field, or
Yeah, exactly.
which is now varying slowly in space.
Yeah.
And so maybe you could have modulation of these properties, which I'm describing, are affected by each field. Yeah, yeah, I think you could see something interesting there. So in the case of like graphene, there's sort of no degree of freedom in the vertical direction.
No.
In a sense. And so now when you introduce some non-uniformity, that just gives you like another property which is varying slowly in space. And I could imagine that leads to different effects. It's hard for me to anticipate what they might be a priori.
You haven't looked at it yet.
Yeah.
Okay.
Yeah, but I think it would, potentially be lead to some interesting, like, unique things. Yeah.
Okay. Yeah, thanks.
Yeah.
Marcus,
Well, I think Daniel can go first.
Just from curiosity, you mentioned in the beginning the magic angle that everybody looks at and that you are quite far away.
Yeah.
On the inside, is there a big difference in what the observations are and the theory is as a function of this magic angle? Is it important or not? Or?
Yeah, I think so. So like in the previous studies, often superconductivity is observed, which is not, we don't see any evidence of that.
Yeah.
And on the calculation level, well, I don't have any plots of how the band structure changes with angle, but I can say it changes by quite a lot. So yeah, it is very sensitive.
And was it the aim to change the magic angle by this, or was this an experimental accident that you thought was happening?
Well, I mean, probably the latter, probably the latter. So it's kind of like, this is what we had, let's take a look at it and see what's going on. Yeah.
Nice.
Yeah.
So Marcos is online as a question. Marcos, can you unmute yourself?
Oh, yeah.
Yeah, I don't know if you can hear me.
Yeah.
Yeah, cool. Paul, really cool talk. I have a question specifically on the last part that is saying for an orbital magnetization to occur, because everything that you've shown, you have to apply magnetic field to actually separate the contribution from the opposite orbitals or opposite valleys.
Yeah.
But now for twisted bilayer graphene has been shown that you can get let's say orbital ferromagnetism with zero field, right?
Yes.
Do I understand correctly that your reasoning for that is an inhomogeneity in the sample?
No. So it's more that, like, if I assume that there's an spontaneous orbital magnetization, and there's some disorder as well in the sample, that it could be that the nature of the orbital order, such as its stiffness or other properties associated with its order, may be changing in space according to this disorder. So it may have some inhomogeneous properties to its orbital order.
I have a bunch of more questions, but maybe I can ask tomorrow.
Yeah, sure. Yeah.
Thanks, Marcos. See you tomorrow then. More questions over here? If not, then I think we should thank Paul again for a very nice talk.